Okay, I'm going to be doing a growth example application word problem from section 5.6 just to help you guys out in doing exponential growth problems. Okay, so this is actually number 6 from your textbook. I actually kind of copied it in to this Word document. In May 2010, a 1932 painting, Nude Green Leaves and Bust by Pablo Picasso, sold at a New York City art auction for $106,500,000 to an anonymous buyer. This is a record price for any work of art sold at auction. The painting had belonged to the estate of Sidney and Francis Brodie, who bought it for $17,000 in 1952 from a New York art dealer who had acquired it from Picasso in 1936. Okay, assuming that the value a sub 0 of the painting has grown exponentially, find the value of, this is part A, find the value of k and determine the exponential growth function assuming a sub 0 equals 17,000 and t is the number of years since 1952. Well, first of all, this is quite an exponential growth because it was only 17,000. Let me highlight these. It was only 17,000 in 1952. Where in 2010 it was 106.5 million. That's quite a jump. So this is not only exponential, this is very exponential. Okay. Now, so for part A, you'll notice that they give you some information that is very important. That is right here. T is the number of years since 1952. That is very important because you have to know where does time start for these problems. In this case, it's 1952. They also told you that a sub 0 is equal to 17,000. This is not information you necessarily need, actually. They give it to you, but you don't necessarily need it. Now, let's start this again. Oops, get out of there. We don't need you. So what we're going to do is, because this is an exponential growth problem, we're going to use our exponential growth equation that we learned in the lecture, which is p of t is equal to p sub 0 e to the kt. Now, notice here they use a instead of p, which is okay. But so to stick with their letters, really in this case a, which I would assume would mean amount, a of t is equal to a sub 0 e to the kt. Now, t is equal to 0 for 1952. And because we already knew that it was 17,000 in 1952, they didn't have to tell you this. That when t is equal to 0, then wherever the amount is going to be the initial amount. So a sub 0 is 17,000. Again, they didn't have to really tell you that. You could have known it because they told you for 1952 was t equals 0. The other thing they tell you is that in 2010, this is what I have in green here, in 2010 it's 106.5 million. Okay. Now 2010 of course is not t because t is the number of years after 1952. So 2010 is t would be 2010 minus 1952, which is equal to 58. Okay, and that gets you 106,500,000. Okay, so now let's put this, this, and this all into this equation. So 106,500,000 is equal to 17,000 e to the k times 58. And then we're going to solve for k. Now when you solve for exponential equations, the first thing you have to do is you have to divide out the coefficient on the right side, or whatever side it might be on. This has to be divided out first. So we will divide that out. Okay. I'm probably not going to divide this. Don't want to divide this unless it divides out evenly. Watch out for dividing this because we don't want to round our work. We can cancel out some zeros. We don't have a problem with that. But you don't really want to divide this out and write a decimal because you'll probably end up rounding. So I'm going to leave it as 106,500 divided by 17, and that equals e. And I'm going to not write k58. I'm going to write 58k now. Okay. Then we're going to take the natural log of both sides. We do the natural log because we're dealing with the exponent e here. And it will save an extra step than doing the common log. Natural log e to the 58k. Let's scroll down a little bit, give us some more room. Okay, why do we do that again? Because this becomes an inverse operation. We are doing a log base e of an exponential e, and they technically go away. Okay, it leaves you just with this. So we have the natural log of 106,500 divided by 17 is equal to 58k. So to find k, we divide by 58, all this by 58, and then we figure out what this is. So I have my calculator here. This is a TI-83. All the buttons are the same of what would be in a TI-84. So let's go ahead and solve this. So this will be the natural log of 106,500 divided by 58. Oh, nope, divided by 17. Then close the parenthesis and divide that by 58. This is actually going to give you a very large number, relatively speaking, for k. It looks small. And we're going to run this to like 4 places. 0.1507. That's actually very large for k. K 0.1507. That's point. Is usually very, 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 very small. So that answers the first part. Find the value k. The next part is determine, I'm reading back here at part A, determine the exponential growth function. So all we do is just recopy our growth function, but now we just insert k where k belongs. So this is a of t is equal to 17,000, that doesn't change, e to the 0.1507 t, and that's our exponential growth function. So there is k, and here is, whoops, our exponential growth function. And now we're ready to do part B. Part B says estimate the value of the painting in 2020. Well, this is just an evaluation question. So now that we have our equation, now we're just going to be given a new value of t. T is not 2020. T is equal to 2020 minus 1952, which is equal to 68. Okay, so now we're going to find a of 68. A of 68, function notation, is equal to 17,000 e to the 0.1507 times 68. Now, of course, with the graphing calculator, you can do this all in one step. Move this over. So we have 17,000 e, that's second function natural log, to the 0.1507 times 68, close your parentheses off, so it looks something like this. Hit enter. And we have this really big number. So A would be equal to, I have this written down, 479,650,668 and 50 cents. You should round. You should go to 2 places on this because we're talking money. And there is part B. Part C says, what is the doubling time for the value of the painting? Well, that's just a formula. It looks complicated, but it's just a formula. Scroll down a little bit more. There we go. The doubling time formula, this is part C. The doubling time formula is t equals a natural log of 2 divided by k. So in this case, it's just the natural log of 2 divided by rk, which is 0.1507. And this is going to give us our doubling time. So we'll punch this up here. The natural log of 2, only the natural log of 2, so make sure you close that off, divided by 0.1507. And that gives us 4.5995. So we're going to say this is about 4.6 years. Make sure you do your label. Okay, and that makes sense because in 2010 it was only 106.5 million, I do believe, and by 2020 it was already almost quadruple that. It's near 480 million. So it had to take less than 10 years for that to happen. Okay, part D is, after how long will the value of the painting be 240 million, assuming there's no change in the growth rate? So that is A. So A is equal to 240 million. Okay. Okay, and what we have to do, oof, don't that, I want that, is we have to find T. When. When is the question being asked. Okay, So this means that 240, 1, 2, 3, 4, 5, 6 is equal to 17,000 e to the 0.1507 t. And now we need to find t. Okay. Well, the first thing, again, we solved this problem just like we solved this problem up here. Just like we did this one up here, we do the exact same way. So we have to first divide out by 17,000, and then we solve for t. So first we're going to divide out by 17,000 to cancel that off. And again, we can cancel out some zeros, but don't round this. 240,000 divided by 17, and this is equal to e to the 0.1507t. I'll just go up here next. Okay, now we take the natural log of both sides. So 240,000 divided by 17 is equal to the natural log of e to the 0.1507t. Those go away. So we have the natural log of 240,000 divided by 17 is equal to 0.1507t. And then we divide by 0.1507, because all we're doing is solving for t. Divide all this by 0.1507, and then now we number crunch. Let's move this over here. Okay, so we're going to do the natural log of 240, 1, 2, 3, divided by 17, close that off, and divide that answer by 0.1507. Enter. 63.4 years. Now remember, 63.4 years. That's after 1952. So then to actually find the year, we take 1952 plus 63.4, and this gives us approximately in the year, what is that, 1952 plus 63 is 2015, I do believe. 1952 plus 63.4 is, yeah, 2015. So in 2015 or 2016, I'll accept either of those answers. And that finishes the problem. So this is a good problem because you had to find k. So and you do the same thing for all the problems to find k. You had and then you had to do an extrapolation. In other words, further into the future, how much would it be worth? So that's just plugging in a t. That's good. We found a doubling time. That's good. And then here, solving for a new value of t, given k with a new amount. So you had to do a lot of problems here. Okay, and that's why I think this is a good problem to do. Again, look for these matching coordinate points there and there. 0, 17,000. Time I'm talking about. 0, 17,000. 58, 106.5 million. That's going to help you get k. Because if you can't get k, you're not going to be able to do any of this. Okay, thank you for watching.